Today I'm going to talk about mathematical aspects of coding theory. So the main application, as you can see, the words coding theory. So it is used in information theory in the following sense. So whenever some data is transmitted through a channel, so it is likely that there are some noises in the channel, and that would cause some errors in the transmitted message of the transmitted data. Now, the motivation of having this theory of priority is to detect the errors that are caused because of these noises, and also, if possible, not only detecting them but also correcting them. So one way of achieving this is to add some redundant digits to our information or the message that we are transmitting, and hoping to get the original message back using that redundant information. So here is an example that we almost see in a day-to-day basis. This is called an ISBN. So what is an ISBN? So there are two types of ISBN. So one is called ISBN 10 and another is called ISBN 13. So ISBN 13 is the most current model that is being used today. And ISBN 10 is still in use, but not as much as ISBN 13. But if you go to some book selling websites, for example, Book Depository or even Amazon, I think they will have both the ISBN numbers. So if you ever try to understand the meaning of the codes that are given at the end of the book, at the last page of the book, here is how things stand. So I'm going to talk about ISBN 10 and not ISBN 13 because ISBN 10 is closer to what we are going to talk about today. So let us stick to ISBN 10. So it consists of 10 digits. So let's say A1, A2, A3 up till A10. So now A1, A2, A9, they could take values from 0 to 9, whereas A10 can take value, let's say 10 also, but to keep the string a 10-digit number, it is often written as X. So how are ISBN codes made? So the first 9 digits, A1 till A9, they consists of some information about the book, where it is printed, where it is written, etc., where it is published, and and the last digit is a check digit. So how was this A10 determined? So A10 is the unique integer between 0 and 10 that satisfies the following property: A1 plus 2A2 plus 3A3 plus 4A4 plus etc. 5A5 plus 9AN should be congruent to A10 modulo A11. Equivalently, if you would just put this A10 on the left hand side in the first equation, you will get an equation like A1 till 9 A9 minus A10, and minus A10 when we compute modulo 11 is same as so minus A10 is same as 10 A10. So equivalently, A10 has to be chosen between 0 and 10 in a way so that the equation that I have just mentioned is satisfied. It is seen that ISBN can detect a single error or a transposition error. So what is a transposition error? So if your code is A1 till A9, the first 9 digit, and suppose you have actually transposed two elements, suppose you have written A5 instead of A3 and A3 instead of A5, then it can detect that. However, there could be many other errors that this ISBN code is not capable of detecting. But if there is a single error or a transposition error, it can detect that error. But we must admit that this ISBN code has uh, no possibility of detecting, uh, or even if it detects an error, there is no possibility that it could correct an error. But it is not as such needed. After all, if you were a librarian, if you were entering some information about a book in your system, and your computer complains that you might not have correctly entered the ISBN uh, the correct ISBN. So then you could just read those 9 digits and then correct it as such. So here is another code that we use in our day-to-day life. This is called repetition code. So how many times it has been seen that when you wanted to say something to your friend, he or she did not understand the message, then you repeated the message 3 times, and somehow you got to agree that what is the correct message. So suppose that I want to send a binary message, so which is most often a computer would send to another computer. And suppose our message consists of 4 digits. Let's say our message is given by 1011. So instead of sending this message 1011, let me send the message 3 times, 1011, 1011, and 1011. Now I have given 2 spaces between this block, so to speak. So now the thing is, if you have received this message from me, 1011, 1011, 1011, and if there is one error, then the error could be uniquely contained in exactly one of these blocks. So then you could actually detect it. And so the error is contained uniquely in one of these blocks, and then the other 2 blocks remain unchanged. So this is kind of a maximal likelihood way of seeing it. And you would like to see how many blocks there are consistent. So then you will choose them. But then you see that this is a very time consuming procedure. If you wanted to correct 2 errors, then you have to send your message 5 times. If you had to correct t errors, you had to submit you had to repeat the message 2t plus 1 times. So what happens if you want to correct t errors? So suppose that when you have transmitted this message, t errors have occurred, then the t errors would be contained in at most t blocks. And then at least t plus 1 blocks will be unaffected by the noise. And you could just see which is the correct message. Even though this is time consuming and hence probably not so cost effective as well, it can detect errors, and if it detects error, then it can also be corrected. The errors can be corrected as well. So now, with these 2 examples, let us now formally define what is a linear code. So now let FQ be a field which has Q elements. So what are examples of finite fields? So very basic examples of finite fields are Z mod PZ. You should know that there are various other finite fields, but let me not go into the study of finite fields today. And instead, I would like to conceive that after this talk, you will be intrigued to see some notions and properties of finite fields by yourselves. So suppose that if Q be a finite field with Q elements. Uh, if you know what are the possibilities of Q, it is very good. Otherwise, I can just tell you that this Q is always a power of a prime number. But other than the Z mod PZ, none of them are of this form, Z mod QZ. So an NKQ linear error correcting code is a k-dimensional linear subspace of the vector space FQ to the power n. So you have a field FQ, and you consider the Euclidean space, so to speak, which is n times product of FQ, and you just take a k-dimensional subspace of FQ to the power n. Needless to say, k is always less than or equal to n. Otherwise, you are not going to actually find an NK linear error correcting code. And this n is called the length of this code, k is called the dimension of this code. And the elements of the code C are called code words. So now suppose that NK has C is an NKQ code. So then there would be k vectors which will span this NKQ code. So k vectors or k code words, whatever you want to call them. So suppose we have k code words that will generate this code. And we could actually write a k by n matrix G, whose entries are of course in FQ, and the rows are the code words that generate this code C. So this matrix is called the generating matrix. You know from your knowledge in linear algebra that such a matrix need not be unique, and they could be actually so you could actually take two generating matrix which will differ by taking a product with a k by k invertible matrix. So now suppose that there are two elements, two vectors or codewords in fq to the power n. After all, fq to the power n is also a code. So let us call the vectors codewords from now on. So suppose I take two codewords. First one is given by n coordinates x1, x2, xn. Let me call it x. The second one y1, y2, yn. We call it y, and we have to somehow define a distance between them. Now, what could be more organic than to define the distance as follows? So, given two code words, for our purpose, what only thing we are interested in is the following. So, how many coordinates do the code words differ from each other? So, we define that as their Hamming distance. We denote this Hamming distance by d suffix h of x comma y. So, this is of course a function of x and y, where x and y are 2 points, and it is defined to be the number of coordinates I from 1 to n, where xi is not equal to yi. Now, if you have read about metric spaces, so you could somewhat easily check that this Hamming distance is actually a metric on fq to the power n. And one of the important takeaways, or of course, one of the important axioms that you have to check for this is that this metric satisfies the triangle inequality. But I believe that you will check it for yourself if you are interested. So another notion that we are going to define for our purpose, specifically for linear error correcting codes, is a notion of Hamming weight of a code word. So if x is an element of fq to the power n, so this is a typo. The Hamming weight of x is given by the number of places, the number of coordinates where x differs from 0. So number of I such that xi is not equal to 0. So we are basically counting, or we are basically trying to measure what is the distance of the point x with the origin. So there are some more important definitions, but there are not so many that I'm going to talk about today. This is something called the minimum distance of a code C. So this is invariant of any code words. This is just dependent on the code itself, C. We denote it by E of C. So what we do, so we take all pairs of code words X and Y, which are distinct, and we compute their Hamming distance. What we do is that we take the minimum of all the numbers that we have thus obtained, and that is called the minimum distance of C. And now we have also defined Hamming weight, so there should be something called minimum weight of C as well. We simply define the minimum weight of C to be the minimum of Hamming weight of all the non-zero code words that are contained in C. Now, using the property of C being a linear subspace of fq to the power n, one could show easily that the minimum distance and the minimum weight of a code are actually the same. And if we have a code C, which is an nk code, namely it has length n, dimension k, and minimum distance d, then it is called an nkdq code. So we have just recorded this information, minimum distance, in this information in the definition. So please feel free to stop me in between if you have questions. So now let us try to understand how messages are encoded and where the error occurs and how do we rectify it. So the first thing is encoding. So how do we encode our message? So Suppose that C is a linear code, and let us for the time being fix a generating matrix which is G, and we define the encoding map. Just to keep parity, I have called it E. So it is a map from fq to the power k to fq to the power n. How is it defined? So you just take the row vector x, which is given by x1, x2, xn, and you send it to x times G. So so you take a row vector x, x1, x2, xk, and you send it to x1, x2, xk times G. So you see that this x is a row vector, so this is a 1 by k vector, and G is a k by n matrix. So the multiplication is well defined, and you are going to get a matrix of so you are going to get a row vector, so that is a 1 by n matrix. So if you have actually encoded a k digit message into an n digit message by uh, by multiplying the message on the right hand side by the generating matrix that we have fixed to begin with. Now G has rank k, and that would ensure that this map that you have taken is a 1-1. Fair enough. So now what do we do? So now the following diagram that I have drawn here actually gives us a way of understanding how messages are encoded, sent, and then how do we retrieve it if it is at all possible. So first we start with an n digit, a k digit message, which is of course an element of fq to the power k. We encode it by the map that I have just mentioned above by multiplying to the right hand side by G. Then we just transmit the message. So an n digit message will go to an n digit message. So this is not really a mathematical map, but this is something that happens through a channel. There would be some noise that must be occurring here, or that might be occurring here, which may flip some of the digits, which may change some of the digits completely. But then we have to come up with a very good decoding algorithm so that I could get back the original message, which lies in this fq to the power n, which is the encoded message. Now, since this since this encoding is a 1-1 map, if we can identify the correct encoded message here in this fq to the power n, we could actually come up with the original message, which is a k-bit message. So this operation is called unencoding, which is a trivial thing to do. But the non-trivial part is to do this decoding. So unfortunately, it will not be possible to talk about many decoding principles, at least in this lecture, but I would try to give you examples of some good codes that are used and that are also very interesting from our mathematical point of view. Okay, so let us proceed. So now the question is, when we define a code, then we mention the length, we mention the dimension, and we also mention the minimum distance of the code in its definition itself. So why is it so that these three parameters are so important? The first thing is length. Why is length important? You can see that if the length of a code is very small, then you cannot encode large messages into this code. So we need the code to have larger length. What about the dimension? See, the dimension of the code is k, and we are trying to encode a k digit message into an n digit message. So you can actually think that we are trying to add extra n minus k bits or n minus k redundant digits every time we send a k digit message for our encoding purpose. But we do not want to add too many redundant digits, because what is the point? That will actually make the process time consuming and not cost effective at all. So then we want n minus k to be rather small, and also we want equivalently k to be rather large. So the n should be large, k should be large. Now here is a rough idea of how we can decode a received message which possibly have some error. So now suppose that I have our code C, which is an NKDQ code. So we show that this minimum distance actually determines the number of errors that could be detected and corrected. And the study that I am going to tell you about will show you that not only the number of errors that can be corrected and corrected is an increasing function of this D. So first, what we do is that we take a positive integer t and we take a point x in fq to the power n. We define a neighborhood for a ball of radius t. So in a usual way, so you take btx to be the set of all y in fq to the power n, such that dh x comma y is less than or equal to t. So now suppose that we have two code words C1 and C2. You can see by triangle inequality that the balls of radius, the greatest integer function of d minus 1 by 2 of C1 and the ball of radius d minus 1 by 2 of C2 will never intersect. So this follows from the triangle inequality. I have mentioned at the beginning that our distance function is actually a metric on fq to the power n. So thus, if the received message consists of at most this greatest integer function of d minus 1 by 2 errors, then the received message will lie uniquely in one of these balls around one of the points in our code. So then you know what is the point C which lies in the ball, and then you could say that what is the original message. So in particular, if there are at most d minus 1 by 2 errors that occurs during our transmission, we can actually correct them. So the moral of the story is, if we have an NKD code, we will call them a good code if n is large and also k and d are large with respect to n. So k being large with respect to n will save us time and money. And of course, if d is large with respect to n, then we can correct more and more errors. Now, one may ask that if I fix a value of n, then can we have k and d to be as large as we want? Of course, they have to be less than or equal to n, but then is it possible that both of them are equal to n minus 1, which will be the best case, I suppose? The answer is actually given by something called a singleton bound, which says the following. So if you have an NKDQ code, then k plus d minus 1 is bounded above by n. So then you cannot have k and d arbitrarily large, and one has to somehow optimize the values of k and d in order to produce good codes. But how do you do it by hand? So it is not very easy to do that, unfortunately. So how do we prove the singleton bound? This is not very difficult. So let me actually show you a proof. So C is our code with minimum distance d. So C is a code which consists of code words which is non-zero at least d of the coordinates. So I construct a space which is generated by E1, E2, ED minus 1, which are the usual basis vectors of fq to the power n. So you see that the dimension of the space that is generated by these vectors is actually equal to d minus 1, and all of the code words that you have in this code that you have just produced, which is d, will have Hamming weight less than or equal to d minus 1. So that means none of the non-zero elements of d will ever belong to C. So C and D, these are two subspaces of fq to the power n, and they intersect at only the zero vector. As a consequence, we can see that the dimension of C plus dimension of D is less than or equal to n. What is dimension of C? Which is k by definition. Dimension of D is equal to d minus 1. So k plus d minus 1 is less than or equal to n. Now a code for which this bound is attained, that is n is equal to k plus d minus 1, is called a maximum distance separable code, or it is simply called an MDS code. One would like to ask at this point, is it possible to construct an MDS code? Of course, one idea is that if you cannot construct an MDS code, then such codes will not be given a name. So here is an example of an MDS code. This is called a Reed-Solomon code, or a generalized Reed-Solomon code. This is the name varies from authors to authors, but here is how they stand. So again, we assume that FQ is a finite field with Q elements, and R denote the polynomial ring FQX in one variable. The variable is X, and all the polynomials have coefficients in FQ. We fix a positive integer U less than Q. So this is for some technical reasons, and if you want to understand it, I have to go a little deep into finite fields. That is not the purpose of this talk. So let us assume this as a black box that I would always take U to be less than Q. And I will denote by R less than or equal to U to be the vector subspace of R, which consists of all the polynomials of degree at most U. Now, what we do is that is the following. So you take a polynomial and you could always view this polynomial as a function of FQ. So given an element in FQ, you can evaluate a function. So you take an element f of a small f of x in R less than or equal to U, and you take an element, let's say a from FQ. You could always write down what is f of x just by replacing x by a in the expression. So keeping this in mind, we fix an ordering of Q elements in FQ and we call them F1, P1, P2, PQ. And now we define an evaluation map from R less than or equal to U to FQ to the power Q, which is given by the following. So I take a function, I take a polynomial f, and I send it to the string f of P1, f of P2, f of PQ. One can easily check that this map is injective, and because we have made this assumption that U is less than Q, it follows that this map is an injective map. So injective map needs actually this condition U less than Q, but it is very easy to check that this map is a linear map. And since we have this condition U less than Q, you will see that this map is injective. So now this R less than or equal to U is a vector space, and we have a linear transformation which is denoted by E. So a vector space to a vector space, we have a linear transformation, and the image of the linear transformation will be a subspace of FQ to the power Q. So E of R less than or equal to U, the image of R less than or equal to U will be the subspace of FQ to the power Q. So it is going to be a code. It is going to be a linear code. So length of the code is going to be Q. The dimension of the code, since this map is injective, will be actually the dimension of this vector space R less than or equal to Q, which is of course given by U plus 1. So what is a basis of this vector space? So 1x squared up to x to the power U. So there are exactly U plus 1 elements. How do we compute the minimum distance? So first, we should know how to compute the weight of a code word. So what is a code word? A code word C is evaluation of a polynomial. So to compute the weight, we have to look at the number of coordinates where the function, where the polynomial does not vanish. So given a code C, which is eve of f for some f, to compute the Hamming weight, we need to compute what are the points, or what are the number of points in FQ where the function, where the polynomial does not vanish. And now you have a polynomial. So you have a non-zero polynomial of degree at most U in one variable, and you want to see at how many points it will not vanish. So it is equivalent to asking at how many points it will vanish. And we know from maybe our first year BSc mathematics that if you have a field, and if you have a polynomial in one variable of degree at most d, and the polynomial is non-zero, then it cannot have more than d zeros. So that means the weight of a code word is bigger than or equal to q minus u. And you can also easily produce polynomials of degree u, which will have exactly u many zeros and consequently q minus 1 many non-zeros. So the minimum distance of the code is equal to q minus u. So you could now easily check that k plus d is what? K plus d is u plus 1 plus q minus u. So q plus 1, which is the length of the code plus 1. So this is an MDS code. So there are examples of other MDS codes, which are also called extensions of the Rig-Solomon codes, but let us not go into that because I have to introduce the notion of projective space if I want to do that. Okay, so here is an important notion which is often useful. This is called a parity check and the dual of a code. So on fq to the power n, we define a scalar product or a dot product, which you do usually in your vector calculus. So take two elements c1, c2, cn and d1, d2, dn. We define c dot d to be summation ci dl. So c1 d1 plus c2 d2 plus cn dn. And we define the dual code of C, which is denoted by C per. This consists of all the code words from fq to the power n, such that c dot d is equal to 0 for all elements small c in DC. It is easily checked that C per is a linear subspace of fq to the power n. The dimension is n minus k. It follows from rank nullity theorem, for example. And the dual of a dual code is itself not isomorphic to, but it is exactly itself. And the generating matrix for C is C part is called a parity check matrix of C. So if H is a parity check matrix, which is of course going to be an n by k times n matrix, it is going to satisfy the equation G times H transpose is equal to 0. So G was the generating matrix of our code. Let us see how it is used. So let us apply our whatever we have learned up till now to the ISBN codes that I started with. So ISBN code is a code of length 10 over F11. So what are the dimension, minimum distance and dual of ISBN code? So you see that a 10-digit code word A1, A2, A10 is a valid ISBN code if and only if it satisfies the following conditions. A1, A2, A10. So this is a row vector times the column vector 1 to 10, that must be equal to 0. So this matrix that we have H, which is given by 1 to n, this is a parity check matrix for the ISBN code. So the dual of the ISBN code is generated by is a subspace of F11 to the power 10, which is generated by this vector, this row vector 1, 2, 3, 4 up till n. So what is the dimension of this ISBN code? So if the dual has dimension 1, then the original code will be of dimension 10. And now you see that the ISBN code will never contain a code word of weight 1. So if all of the coordinates except for 1 is non-zero, then you see that this product is never going to be 0. So the minimum weight has to be at least 2, and one can produce a code word of having weight 2. So for example, if you take this code word 1001, so how would it stand? So 1 times 1, in the middle all the products are going to be 0 because here all the terms are 0, and then at the end you have 10. So you have 1. So you will multiply it by 10. So 1 times 10 is 10. And then you are going to add it to 1 that comes from the first coordinate. And so you have produced a code word of having weight 2. And consequently, the minimum distance of or the minimum weight of the ISBN code is 2. So now I would like to leave it as an exercise if you have become interested in this topic to compute the length, dimension, minimum distance, and dual of our repetition. So let me now invest into some more non-trivial examples. So this is actually a generalization of Reed-Solomon codes. So this is called a Reed-Muller code. So instead of considering polynomials of one variables, why not we consider polynomials in multi-variables? So let's say m variables. So I take fq x1 x2 xn, call it r. I fix an integer u again, and again for technical reasons, I assume that u is less than q, and I denote by r less than or equal to u to be the subspace of r that consists of all the polynomials of degree at most u. So again, just like before, and of course, here we introduce one more notation. This n is the cardinality of fq to the power n. So this is equal to q to the power n. So then we fix an ordering again, just like we did for the case of Reed-Solomon codes. So and then we define the evaluation map as we have done in the case of Reed-Solomon code. So you take a polynomial, you can view this as a function on fq to the power m. So if you pick a point p1, for example, you compute what is f of p1, you just write it, and then you form the string f of p1, f of p2, f of pn. Now one can show that this is an fq linear map, which is very easy to see. And again, the condition that u is less than q will imply that this map evaluation is an injective map. So how do we compute the important parameters? So for example, what is the length? Length is clearly n, so there is no doubt about it. What is dimension? So now since this map is injective, the dimension of the code is going to be the same as the dimension of r less than or equal to u. So r less than or equal to u is the vector subspace which consists of polynomials of degree less than or equal to u. It is spanned by monomials of degree less than or equal to u. How do monomials look like? X1 to the power I1, X2 to the power I2, Xn to the power In, where the sum of uh, all the exponents that we have is less than or equal to u. So ultimately, this boils down to computing this number that we have here, this cardinality of this set. Well, I could use one more slide, but I'm really running out of time. But let me give you the final answer, which is m plus u choosing. So the code is of length n, which is q to the power n, and the dimension of the code is m plus u choosing. How do we compute the minimum distance? So this is what I really wanted to emphasize. Okay, so now how do we compute minimum distance? So you take a code word, you have to compute its weight. How do we do that? So a code word corresponds to a polynomial in n variables, let's say f. So c, if c is our code word, then it looks like f of p1, f of p2, f of pn. What is the Hamming weight? It is the number of i's where f of pi is not equal to 0, which is equivalent to saying that it is the number of points or the number of elements of fq to the power n where f of p is not equal to 0, which is again equivalent to saying that this is equal to n minus the number of points of fq to the power n where f vanishes. So now just a remark here. So if I want to compute the minimum weight, I have to compute the minimum of this quantities with c not equal to 0. So I have to compute the Hamming weight of all the code words, all the non-zero code words, and then I have to take minimum. And if I have to take minimum on the left hand side, then on the right hand side, in this cardinality, I have to take the maximum. So the moral of the story is the following. So I have to compute in order to compute the minimum weight of a code word, I have to compute what is the maximum number of possible zeros that a multivariable polynomial may have in fq to the power n. Now here fq to the power n saves us, because if you take, for example, a code of, so not a code, but a polynomial in two variables, let's say y minus x squared, and suppose our field was r or even q, so then you could see that it has infinitely many solutions, and then asking what is the maximum number of zeros will not make sense, because you cannot take maximum of infinite sets, or if there are quantities in the set that are actually infinite. So but here, since our field is finite, fq to the power n itself is a finite set, and as a consequence every polynomial will have only finite number of zeros. So then can we compute this maximum? So if I take a polynomial which is non-zero, of course, then what is the maximum possible number of zeros that this polynomial may admit in fq to the power n? Now this answer goes back to someone called Ord, who was a Norwegian mathematician. In 1920s, he proved this theorem. So if d is less than q, then and if you take a non-zero polynomial f of degree d, then the number of zeros is bounded above by d times q to the power n minus 1. So to the hosts, how much time do I have?
You can have 5 more minutes.
Oh, thanks. So then what we do to prove it is to use a double induction on a and b, or alternatively we could use an induction on the quantity a plus b. So let us do that. Many of you might not have seen how double inductions are used. So let's see how can we prove this inequality using an induction on m plus d. So m plus d is equal to 1. So the only possibility is m equal to 1 and d equal to 0. The other possibility, of course, is m equal to 0 and d equal to 1, but the polynomial does not have a variable. So what kind of a polynomial is this? So we do not consider that. So we take this m equal to 1 and d equal to 0, and the assertion is trivial. So a polynomial in one variable of degree 0 is a non-zero constant polynomial which has no roots, and the right hand side is also 0. So that takes care of this case. And suppose that our assertion is true for all the smaller values of m plus d. So you take polynomials in some number of variables of some degree such that the number of variables plus degree is less than the same plus d. And suppose that our assertion is true for all such cases. Let us now take a polynomial in m variables and degree d. So this should be equal to d, not at most d. And we distinguish two cases. The first case being the following. So there exists an element a in fq such that x1 minus a divides this polynomial completely. So I can write f of x1, x2, xn as x1 minus a times some GA times x1, x2, xn. GA denotes the quotient of this polynomial when it is divided by x1 minus a. Note that this degree is additive when we multiply, and as a consequence, this GA is a polynomial in m variables, and it is of degree d minus 1. So the number of variables plus degree is equal to m plus d minus 1, which is of course 1 less than this. So the induction hypothesis applies, and we could do the following. So how do we compute the number of zeros? So a point is 0 of this polynomial f if it is either a 0 of x1 minus a or a 0 of GA of x1, x2, xn. So we just add the number of zeros of these two polynomials, x1 minus a and GA of x1, x2, xn. Okay, so x1 minus a, how many zeros does this polynomial have? So the first coordinate has to be a, and the other coordinates can be anything. So there are q to the power n minus 1 options. On the other hand, for the next set, the induction hypothesis is applied. So we have a polynomial of degree d minus 1 in m variables. So this is less than or equal to d minus 1 times q to the power n minus 1. If we add them up, we get the quantity as desired. Next, suppose this is not the case. So maybe I'll leave this. I'll of course share the slides with the hosts, but it is not very difficult either. But I would rather leave this. But the point is, one could prove this, and one could also show that not only this is an upper bound dq to the power m minus 1, we could also produce a polynomial which has exactly d times q minus 1, d times q to the power m minus 1 many zeros in fq to the power m. So this is actually the true maximum. So the maximum number of possible zeros of a polynomial of degree d, of course the polynomial is non-zero, is equal to d times q to the power n minus 1. How do we apply this to a study of minimum weight of the Muller codes? So just from where we stopped in the previous slide. So you could see that the minimum distance is n minus this maximum, and here d has to be replaced by u. So the minimum distance is q minus u times q to the power n minus 1. And as a consequence, the Muller code is a code of length q to the power m, dimension m plus u choose u, and q minus u. So minimum distance is q minus u times q to the power n minus 1. So the last concluding remark is the following. So there is a more general recipe of producing codes, the way we have seen Muller codes and Solomon codes are defined. So we, instead of taking the whole spaces, we take some special subset of fq to the power m, which are called affine algebraic sets or simply affine varieties. We evaluate on them finite dimensional linear subspace of polynomials in m variables. So by a similar technique, we could produce a code. Now note that the length of the code is exactly equal to the number of points that we have on the set that we have already started with. So in general, in most current research, finding affine varieties which has many points have become a very interesting problems, which is of course interesting from its own mathematical point of view, and also from the point of view of coding theory I just explained. And also after you have defined a code using such an affine algebraic set or an affine variety using the way that I have mentioned, to compute the dimension of the code or to compute the minimum distance of the code are actually problems that are studied in combinatorics, algebraic geometry, and number theory. So this is the end of the talk. I hope that you found something interesting in this talk. And thanks again for being attentive and of course giving me this opportunity to present this talk. Thank you.